Thanks for joining us for this month's Best Practices webinar. And this is Rona Palmer from eMaint Enterprises. And I'm really pleased to have with me on the line today Carl Schultz, who's a CMRP and Director of Business Development at SEMEQ Inc. And he's going to be presenting today's topic, From Preventive to Predictive, a PdM primer. Carl, are you there with me?
I am.
Well, that's great. Let me just tell our audience a little bit about you, Carl. Carl Schultz has over 30 years' experience in the predictive maintenance and reliability segment with an emphasis on the PdM side of those practices. And Carl has been responsible for everything from full implementation of PdM programs to the day-by-day technical activities. And he applies reliability engineering skills to take advantage of the links between reliability and predictive maintenance programs. And Carl assists clients in developing and implementing outsourced, fully integrated PdM programs. And Carl, we have, last month we did a session on improving your preventive maintenance, and this seems like, the next step, moving from preventive to predictive. And maybe while we have a pretty large group today, and while they're logging in, can you tell us a little bit about how you got started in predictive maintenance?
Sure. It's actually kind of interesting how I got started in predictive maintenance. After I got out of the service, when I was in the military, my experience was in photo processing, photo finishing in what was known as a reconnaissance unit, pre-strike, strike, and post-strike photography from high-speed jets. When I got out of the service, I had been introduced to thermography, infrared imaging from my father, and my comment to him at the time was that I can make those pictures look better for you. Well, the long and short of it was he had purchased a franchise from one of the earliest infrared imaging camera manufacturers. At the time was Agema, A-G-E-M-A, which somewhere down the line became FLIR. FLIR acquired them, FLIR being the top manufacturers of infrared cameras now in today's PdM world. But after about 16 years, we put together an infrared imaging firm that we ran and operated for about a 16-year period of time. And then after that, I just progressed into various PdM predictive maintenance technologies, using that company experience as pretty much my leverage and base for what got me interested in PdM as a whole. I'd like to cover today. This is just a short agenda of what we'll be highlighting throughout the presentation. What is PdM, the benefits of PdM versus PM, fueling the PdM program and processes through financial savings and other aspects. We will also cover what the top 3 tools are in your PdM toolbox, what you should look for some possible additional predictive maintenance tools, maybe some thoughts on combining these tools, what a good program looks like, how you might want to get started, what tools should you look at first, which one to really kind of optimize to kind of springboard the program. And then where do I go from here? What some of the next steps are, and then maybe some usage to implementation of this PdM program. So the way I've put this together is to look at each one of those subcategories of topics here, and we'll begin with kind of looking at PM versus PdM. So through the next few minutes, discuss what is the definition, some benefits, and then fueling it, fueling the program, fueling the PdM initiative. I do want to make note that the fueling the PdM through financial savings really I've moved to the back for logic purposes of the presentation, so we'll cover that in more detail really at the latter part of this presentation. So PM versus PDM, and what is PDM? You hear the acronym. We're a heavy acronym industry, I guess. Reliability in general throws all kinds of acronyms around: EAM, CMMS, PDM, RCM, FMEAs. You hear them all over the place. So what is PDM? PDM is an acronym that basically stands for Predictive Maintenance. And what is predictive maintenance? Predictive maintenance is the monitoring of assets, carefully watching them, the capability to diagnose what's taking place with those assets at that particular point in time, a diagnostic snapshot to determine the health status. It allows you to forecast what the anomalies, running issues, problems that you may encounter with that asset as you go through each one of the cycles of measurement. It gives you a means to detect deficiencies within those assets, and it allows you the capability to see or understand what's taking place with those assets prior to the functional failure. And we'll discuss more in length what some of these tools are, what each of the capabilities, individual capabilities are. Typically, PDM is a route-based condition monitoring process. And they're analytical tools, scientific tools. The majority of them have been around for a significant period of time, anywhere from 40 to 70 years, depending upon the individual type of technology. And I have the P to F curve up here just as a little bit of a reminder. I think that many who are here and attending today are familiar with the P to F curve. And the objective then of the use of predictive maintenance is to drive yourself up this P to F curve from the right-hand side where you see the functional failure and get yourself living in the green. So if we're using these various technologies, then if you look at the top of the curve, point P, this is where PDM technologies begin to truly come into their own, at the point where we can begin to tell if there's potential failure with any one given asset, provided we choose to go looking for any of those issues. And that's what these instruments in PDM are designed to do, to go looking for any issues with those assets. So some of the benefits then of PM versus PDM. PDM is frequency-based, as is PM. However, a significant difference is that it is not subject to OEM recommendations. PDM actually is predictive maintenance, should be a living program within your organization, driven by the health of the assets and driven by the known frequencies of failures as you develop your PDM program. It also has the capability to assist with multiple cost reduction and or financial gains. As some examples, we have here the possibility of assisting with MRO or stores reduction efforts, maintenance, repair, and operations, stock and inventory. Capability of maybe reducing the volume of bearings that you would keep in stock, the number of electrical components that you might keep in stock. It also will assist with increases in uptime and asset run times, and thereby potentially assisting with the increase in throughput of your individual production lines. And it does have the capability to pay for itself in a significantly short time frame. It allows for sufficient lead time to plan and repair. Traditionally, condition-based monitoring is also significantly less costly to perform than emergency-based maintenance. It's more focused on repair actions. It enables repairs to be done at a time that is most convenient to operations. By having the knowledge ahead of time of what issues might exist with any given asset, you then have the capability of entering these repair items into your planning and scheduling processes, thereby scheduling it for repair at your convenience rather than an emergency failure and having to repair it instantaneously. It'll increase the knowledge and confidence in your equipment health. It extends, or I shouldn't say extends, it assists and allows you to have fewer infant mortalities. And one of the reasons that it allows for less infant mortalities, typically PM type of work that is typically the PM work that we're involved in actually is invasive, intrusive to the individual assets that we're working with. We take typical bearing inspections or electrical cabinets that call for various cleaning and tightening processes. It's a very intrusive process. We're breaking seals to inspect things. We're opening cabinets and tightening screws to given torque levels, which may have been loosened to begin with, so that torque level is now damaging more components within there. Basically, what we end up doing is continuing to over-invade our assets when, with predictive maintenance technologies and tools, they allow us to actually monitor how those assets are running at that particular point in time. And there's an old phrase that lots and lots of us have heard: if it ain't broke, don't fix it. So with the use of PdM tools, you're monitoring those asset healths, and if it's running fine, there's no reason to go out and do a PM on it. The use of these tools also allows for confirmation of the repair itself. So let's say you're just doing some spot checks with PdM, various PdM tools, whether it's vibration, thermography, whatever the case may be. It also gives you the capability of confirming that that repair has been effective. And overall, better operational performance. So let's talk a little bit just about what the top 3 tools might be. Since we've alluded to a couple of them here, we'll talk a little bit about some additional tools and then what some combinations of tools may be. So we'll highlight what the top 3 are first. Really, the top 3 in any predictive maintenance toolbox are going to be vibration analysis, infrared imaging, and oil analysis. And I'll walk you through each one of these individually to cover some of the individual issues that they might find and where they would be primarily used. So in the case of vibration analysis applies to the majority of rotating equipment. It also happens to be one of the most widely used technologies. I think when anybody goes out on the web and searches for PdM, about 99% of the time you're going to get a hit on vibration analysis. There are a number of different types of instruments that can be used for vibration detection and analysis. They range from handheld vibration pens to specialized detectors, all the way down to permanently installed vibration monitors. Now, while vibration pens may seem from the outset to be the way to go to stick in your toolbox, there's definitely some pros and cons to both vibration pens and full spectrum analyzers. From a vibration pen standpoint, they're certainly low cost, compact, and easy to use, and you can compare measurements to established standards or known standards for those individual assets or components within them. And some models have the capability of integrating temperature measurement as a spot temperature. A couple of the cons with the vibration pen certainly would be limited analysis capability, limited adjustability when you're looking at various spectrums and frequencies, and the trending using a vibration pen must be done manually. There's no software capability with a vibration pen. Now, on the full spectrum analyzers, typically what you might see a service provider use or look at for in-house programs. Some of the pros, they're a little bit more sensitive, so they have the capability of maybe detecting nearly all machine faults as compared to the sensitivity of a vibration pen. Multi-channel measurement capability, extremely powerful software for trending and analysis. With the full spectrum analyzer, you also have balancing capability, built-in route management, and bearing measurement data is at times included in those multi-spectrum analyzers. However, one of the largest cons is a relatively high cost of purchase for the full spectrum analyzers. So what are they used for? Primarily used to indicate cracks, pits, roughness in bearings. As we mentioned with the full spectrum analyzer, balance or unbalanced issues in rotating equipment, shaft misalignments, bends and cracks, loose parts or loose foot is typically what you'll hear with regard to how that particular rotating train is mounted. Misaligned or damaged teeth gear, deterioration. It will point to some AC and DC motor and controls problems. However, as we go through this, you'll see there's a couple of other tools that in combined with vibration analysis actually will give you the more of an opportunity to even assess what's going on with the motor and the control centers themselves, drive belt problems, and then resonance as well can be detected with vibration tools. Quick overview of vibration analysis. And again, as Rona mentioned, please feel free to submit questions to her. And if you have questions about specific technologies, uses of those technologies, when we get to the end here, we should have easily, I would hope, 15 minutes or so to be able to do a little Q&A here. So the second tool we mentioned in the top three was infrared imaging or thermal imaging, thermography. Again, a very widely used technology, typically used for electrical inspections. It can be driven by insurance companies. There are a number of insurance companies that offer deductions in industrial policies for the use of infrared imaging on electrical systems. There are a number of different types of instruments for detection and analysis. There's the actual thermal imaging camera, infrared thermometers, contact pyrometers, and thermal stickers or coatings. Thermal stickers or coatings typically are used more, I would say, in an R&D environment. They have been utilized to a small degree in looking at various product and processes. One of the things that comes to mind is thermal forming. In the use of thermal forming, you have the capability of applying a thermal sticker or coating which can change colors or tones when the process actually takes place. When the product is formed, the mold releases, and these thermal stickers or coatings then can give you kind of a topographical map of what the temperatures within that mold might be. Not typically used in predictive maintenance. Thermal imaging cameras and infrared thermometers, spot radiometers, are more along the lines of what we're typically using out of our PdM toolbox. Typically used on problems that would display themselves as a change in temperature, of course. And these can be one of the things that people automatically think about when they think about infrared imaging is, I'm going out to find a hot spot. While that is ultimately what the cameras were and the infrared imagers were initially designed to do, the opposite is true also, in that once you get accustomed to the utilization of this particular tool, looking for cold spots can tell you just as much as looking for hot spots. But typically we're looking at high resistance in electrical connections, excessive friction, which certainly we know that under lubrication, over lubrication in bearings creates that. So you have the capability of seeing in the bearing housings external heat that can be seen with an infrared camera. Refractory deterioration in boilers, for instance, steam leaks, roof leaks, valve leaks, insulation voids if we're looking at the interior or exterior of our facilities. It's a very versatile tool. One of the things I want to make sure that I do remember to point out here in assessing any type of a PdM program and the use of thermography is to make sure that you take your arc flash requirements into consideration when using this tool. The reason that we say that is that using thermography cameras on electrical distribution systems, infrared cameras cannot see through anything. So primarily, low voltage cabinet doors need to be opened while the inspection process takes place. And therefore, we need to make sure that we are very cognizant of our arc flash ratings, arc flash requirements, personal protective equipment that must be utilized when performing those types of inspections on electrical distribution systems. Now, by the same token, electrical cabinets can be retrofitted with IR windows. These windows are built in particular crystallines. Calcium fluoride is one of them, and they are relatively transparent to the infrared energy seen by an infrared camera. So while we do need to take into consideration our arc flash requirements on medium voltage, high voltage gear, electrical gear, there's also the capability of installing these IR windows so that you can still monitor the electrical system fully all the way down through your system, through your electrical system. A couple of other things to take into consideration when evaluating infrared instruments and implementation of those instruments is that it can be sensitive to external influences. For instance, wind blowing across the surface of any target will convectively cool any temperature that you're looking at there. Reflected light within the infrared world of the PdM industry, you'll hear the term emissivity, which I tend to throw out there as East Mississippi. The simple answer, what is emissivity? Emissivity is the amount of infrared energy that any one given target actually, that the infrared camera can see. So there are calculations that can be entered into the camera, calculations that can be entered into software. The point is not to go into a discussion of emissivity, but to be aware that there are external influences from a physics nature that need to be taken into account when using these types of instruments. They can also be sensitive to focus and field of view. And the reality is that there's fairly extensive training that should be required for the use of thermal imaging cameras, especially when the interest is in absolute or accurate temperature measurement of any one given target. And then the last of the top three would be oil or lubrication analysis. Again, a good multi-purpose tool to determine the condition of the lubricant itself, to identify how much, if any, contamination exists within the lubricants that you're using in your assets, identify the quantity and the size and the type of the wear particles. So oil analysis actually can determine the size and the type of particles if you're getting excessive wear from your bearing races, if there are other particulate matter in there. And then it lends itself to creating an atmosphere of changing the oil not on a time-based aspect, but from what is the actual condition of that oil as we're evaluating it. Utilization in gearboxes, transformers, and then any equipment with oil circulating systems. The final note here, supplier oil should be in the analysis program as well. It's important to validate the condition of your arriving lubricants to make sure that they meet your plant standards and the promised deliverable quality from your supplier as well. We like to think that everybody manufactures whatever product they're putting out the door in a perfect nature, but the reality is that any product is susceptible to flaws, and in the case of oil, frequently, I shouldn't say frequently, but there are times when it is delivered with contaminants, with soaps, with other breakdown capability upon arrival. So it's a good idea to really make sure that you put your supplier's oil into your lube analysis program. Measures the physical and the chemical properties of that oil. Degradation of the byproducts in there, what type of oxidization, nitration, sulfates are in there. These laboratory instruments have the capability of determining what the viscosity is, acid number, base number, foaming tendencies, what the volume of water is within oil, and then, as we've mentioned a couple of times, particulate count also. Sampling techniques are fairly critical. The equipment should be at an operating temperature when drawing that sample. Sampling should be done, of course, then during operation while that asset is running. The sample should be representative of oil in the system, never from a dead leg and never after the filter. Naturally, if you're taking it after the filter, you're filtering out the particulate matter, the issues that you're looking for within that oil. So we want to take it where it's representative of the operating conditions of that oil. And the location and the method of the sampling should be consistent. It's one of the reasons you'll hear a number of folks talk about installing sampling ports, specific sampling ports within their assets. So those are the top three, and I'll mention and go through just a couple of other PdM tools here. In particular, ultrasonic testing and motor circuit analysis. Now, ultrasonic testing, airborne ultrasound converts sound to ultrasonic frequencies into audible tones. We have the capability of trending then the sound pressure level in dB in dB measurements. And some of these tools actually have software that's capable of analyzing the signal in an FFT spectrum. One of the real nice aspects of ultrasound is that it's easy to use, requires fairly minimal training. It's very sensitive, and it can be either contact or non-contact, and it's a fairly inexpensive technology compared to the previous three that we looked at. The previous three, the vibration, the full spectrum vibration analyzer, a thermal imaging camera with full temperature measurement capability, and oil labs can be fairly expensive to implement into an in-house type of a program, whereas ultrasound can be fairly inexpensive. It can be utilized to detect problems in steam, air, gas leaks, vacuum leaks, faulty steam traps, bearing faults, especially low-speed applications. You'll find in talking to folks who perform vibration analysis on a regular basis that slow-speed applications can be difficult for a vibration analyst. Ultrasound can assist and lend itself to detection of bearing faults in low-speed applications. Electrical tracking and corona can be heard with ultrasound, pump cavitation, heat exchanger leaks, valves, and hydraulic leaks. The picture you're looking at here in the lower right-hand corner actually is an example, a pretty good example of the use of contact ultrasound in a lubrication program on a slow-speed rotating piece of equipment. The gentleman actually has two capabilities here. He is listening to the grease being inserted into the outboard bearing of this pump so that he can hear the audible tone as the grease is being injected through the Zerk fitting. A real good application of the contact ultrasound. Now on to motor circuit evaluation. You heard me mention earlier that vibration analysis can point to some AC, DC, motor and control problems. Motor circuit evaluation really is your most comprehensive tool for motor health. However, again, it's a fairly expensive tool to get involved in. It detects it has the capability of detecting electrical imbalances within the motor and the insulation system. It is comprised of both online and offline testing. It tests the entire motor, everything inside of that housing, including the insulation. One of the nice things is it uses lower voltages than surge comparisons or mega tests, so the use of motor circuit analysis actually has less of an opportunity to create its own faults. So in looking at online testing with motor circuit evaluation, loose or broken rotor bars, cracked end rings, misalignment, power harmonics issues, voltage imbalances, under or over voltages. And then in the case of offline testing, resistance to ground, turn-to-turn ratio, shorts, winding contamination, phase-to-phase, phase-to-ground impedances, and comparisons. And then also the readings with these instruments can be trended over time to forecast any increased risk of failures. A couple of very, very good tools to add to the top three. One of the aspects that takes place in implementation of predictive maintenance is two can be significantly better than one. They tend to complement each other. I had mentioned earlier that ultrasound has the capability of hearing arcing and corona. So at the same time that you're out in any substation, whether it's an outdoor substation or even an enclosed medium to high voltage 4160, say, switchgear, carrying an ultrasound tool with you as well as the infrared camera, in combining those two PdM tools in your PdM toolbox, is going to give you significantly better coverage to determine what's taking place. Thermography, infrared, cannot see corona. Ultrasound can hear corona, particularly on a high humidity day where your infrared camera is going to have issues seeing problems in the upper insulators or connectors in an open air high voltage substation. Combining vibration and oil analysis. We talked about oil analysis being able to see what the particulate makeup is, determine what the particulate, what particles exist within that lubrication on that asset. So combining oil analysis and vibration analysis together, again, just gives you a much better handle on what's taking place with that asset. So what does a good PdM program look like? We'll talk a little bit about getting started, what tool first. So really, one of the foundational aspects in looking at implementation of a PdM program that is based in proactive maintenance and proactive operations is the development of foundational information. This foundational information includes an asset list, often referred to as a master equipment list, standardized. So standardized by class, subclass, make, model. Criticality ranking of those assets, either A, B, C, D, or a numerical ranking of criticality ranking of those assets. Numerical will give you a more granular look than the typical ABC. But the criticality ranking then will determine what assets you want to go after first. Identify through that criticality ranking on your top players there, what are the most likely failure modes of those assets and what are the most likely causes of those failure modes. And then identify the most applicable and effective maintenance strategies for each mode or cause. Now that can be PdM, it could be PM, or it could be run to failure. Again, another one of those acronyms that we're heavy into in this industry, RTF, run to failure. Any one of these three is a viable strategy, but we need the above foundational information and the evaluation of those failure modes and causes to determine what's going to be our best maintenance strategy. And then identify a confirming PdM technology for each one of those modes and determine whether or not to contract it, perform it in-house, or a hybrid of both. If you're doing it outsourced, they'll create the routes for you. Your suppliers will create the routes for you, but inevitably you need to create routes, set up work orders, and then actually begin the monitoring. And once you begin that monitoring, then you're going to, you've got all of this data that you just worked on. It affects your business performance. It should be standardized, used to generate your reports. Our companies tend to make very large initial investments, whether they're in infrared cameras, vibration data collectors, training. When I was, and I'll go back to this slide here because we're talking about going through that foundational data. What we're talking about here is that that data should form a bedrock for your PdM and reliability programs. So the standardization of it, it's not static, but it should be concise and standardized and effectively used in your programs and processes. And then the next step there then, of course, is to implement this information from both the results of the PdM program as it's dovetailed into your data in your system into your CMMS. Your CMMS is a component of the Enterprise Asset Management System. We talked about being able to plan ahead of time to schedule repair of the assets prior to emergency downtime. So your planning and scheduling begins with the use of this CMMS. And that planning and that scheduling contributes to the overall improvement within your organization. It will impact the bottom line, improve your process, and it contributes to both the PdM program and the reliability program. So where are you going to get your bang for the buck? You're going to review the failure modes and the causes against the confirming technology. Look at it and determine where are the bad actors or recurring problems, downtimes, or bottlenecks. Start there. Start there and utilize that PdM technology against your bad actors. We call it cherry picking in the industry. Anytime anybody implements a PdM program, one of the significant things they're going to find right off the bat is that you're going to have to use some caution in the number of problems that you begin to report on, because if you go looking for things, you're going to find them. And when you find them, you can overwhelm your maintenance department. So start there and use the confirming technology on these bad actors to enhance the learning and the implementation curve on that program. The cost of the technology versus the return on the investment. Do some cost-benefit analysis on it for payback. Even if you can't afford an in-house project, tools on your own are the most expensive technology. Pick some technology that aligns with your bad actors. You don't need a full-blown program to at least get started. Even just taking vibration analysis and having it done on a monthly or a quarterly basis is going to be significantly more beneficial than spot checking from time to time. So where do we go from here? What are some next steps? Uses for implementation. When you want to take this to the next level, now's when you need to start looking at various KPIs. So determine what types of KPIs your organization wants to measure and track. Is the interest in implementation of PdM to look at percentage of labor hours on PdM? So are you spending more labor hours now in a proactive versus a firefighting mode? Percentage of labor hours on PdM results. What's the yield? Or the failures on PdM covered equipment. In other words, how effective is the PdM program? Are we having less failures than we were 6 months, 12 months, 18 months, 3 years ago? Can you apply a KPI to the value of the saves? And then perhaps another KPI is the percentage of planned versus unplanned work. So these are just some examples of KPIs. But you're going to need to support this program that you're putting into place with all of these tools, pick a KPI and track that KPI through the life of the program. Again, another acronym, KPI, Key Performance Indicator. Case histories. You're going to want to take the time to create and catalog case histories. Certainly, your own case histories are going to be the most powerful in any program. However, if you're not involved in a program, if I recall through the poll earlier, 73% of the attendees didn't have a PdM program in place. So you're going to need to go to bat to implement. Here's a couple of starting points that you can get some case histories from. If you go out to the reliability web, maintenance technology, SMRP is another one where you can actually download case histories for individual types of PdM technologies that can support what the efforts are that you're wanting to implement. These are just some examples. Various PdM service providers will also implement or have available case histories for you. So I want to kind of show you the power of what a case history might do. I'll take you through a relatively simplistic one that I put together here. So this is a sample case history of a main control cabinet on a production line. This is, of course, was defined through thermography, infrared imaging. The image on the left shows the initial find. On the initial inspection, the C phase of this particular contactor block was exhibiting a temperature of 421 degrees Fahrenheit on the C phase here, the right-hand side. You can see the little box gives you an output, temperature measurement output there. The image on the right, there was another inspection conducted 12 days later. 12 days later, there was already a 100-degree F rise on that same hotspot. Now go back to very early in this presentation when we talked about the P to F curve, and we said if you go looking for something, you're going to find it. But when you find it, now is when you're starting to slide down that curve. Here is a little bit of an example of how quickly some anomalies can begin to deteriorate down that P to F curve. So the repair was initiated, and the component then was brought down to a reasonable temperature and almost a decrease by 1/2. Now, there may be some out there who have seen thermography and infrared imaging before, might be a little accustomed to its uses and its reports. One of the things I wanted to point out here is that even with electrical distribution in particular, and even with vibration analysis, when you find the main problem that you're initially reporting on within your process and your program here, see my little arrow here, you notice that this leg now, the A phase, actually appears warmer than the B and C phase. The reality of the situation is that that repair was affected, and the next weakest link in this system is now exhibiting itself as a potential problem. So the next monitoring point will show up. Not all of our assets are brand new out of the box, and in fact you'll see in this next slide here what in fact we're talking about with this particular asset. So this repair was made during normal day shift hours. The repair, because it was found ahead of time, was completed in about an hour. The average value of a production hour for this particular line is approximately $10,000 per hour. The maintenance personnel, had it failed in an emergency case, would have taken a minimum of 48 hours to repair this. If you do the math, you're looking at $480,000 opportunity in savings, $470 if you take the 10K out of it that the line was down for an hour. That's not even taking into consideration a failure within this cabinet, the collateral damage that would have taken place. I just mentioned in the previous slide, chasing down the next weakest link. The entire disconnect itself is circa 1966. It's not something you're going to go to the warehouse and necessarily find. Certainly not going to be able to find with all of the parts ready to install. There was surrounding control cabinet components that would have been damaged, let alone associated AC and DC gear, including the drive motors associated with the component. So not only are we talking about the savings in production time that is actually measurable right off of the bat, but we can look at some soft dollars that had availability as well. So this kind of takes us to the next step here. We want to be able to speak to the financial benefits of what we're doing, to be able to sell the program. So using statements like, the increase in production this year that could have been attributed to PdM is X dollars. Or through the implementation of this program, we contributed to a reduction in unscheduled downtime of X through the course of this year. or through the course of the last 6 months. Primarily what I'm trying to get across here is identify how your upper management views a PDM program. Is it from an economic viewpoint? Is it from return on investment? Will it contribute to the corporate bottom line? If it does, show it to them. Are they looking for a reduction in inventory spend or for maintenance and repair, overhauls for your stock? Then this is what you want to focus on for your KPIs. You also need to understand that this program is owned by everyone within your organization, not just if you're implementing in-house or if you're using a service provider. It's not just owned by them, but it's owned by us. It's owned by the people who manage us. It's owned by the shareholders. So communication all the way across your organization. And then, of course, with maintenance and operations for a full understanding of what it is we're looking to implement. We need to be clear and confirm everyone's understanding, and from operations and maintenance, what's in it for them? Are we going to lessen the volume of emergency call-out hours? If so, show them how. Demonstrate the value. If they're feeling intimidated by it, a new technology, we've never done this before, be patient, teach them, show and tell. Share everything that you're finding with them and provide everyone within your organization information and reports. And you need to act as the change agent in teaching folks about the new technologies and the PDM. Become the expert. Show others why it's valuable to the organization and to your reliability effort. Make your efforts visible by communicating and sharing that information. Trend the data and illustrate benefits. This was a program that was implemented, as you can see, in the early 2000s. And you can see that it has been tracked over about a 3-year period of time, actually a little less than 3-year period of time. What the graph is showing us here is the decrease in the number of problems found at each specific plant through the continuing implementation of an effective PDM program. And on a final note, I want to make sure that everyone understands that the reality of any PDM program is that it is only sustainable through continued use of these technologies. Unfortunately, as you begin to implement, as you begin to see these decreases in fines, you will find that somewhere down the line, 3 years, 5 years down the line, whatever the case may be, you're going to end up hearing, okay, well, do we really need that PDM stuff anymore? It is only through the sustainable use of these technologies that you've been able to achieve these results.